start soon, so we don't have to wait so long for lunch again. Okay, so you remember from last time we were talking about universal constructions, and so we introduced the terminal object, the initial object, the product, and then we talked about finite products and how those all interpret respectively the truth, the positive, and then the contexts of intuitionistic logic. Right? So now we need to finish up the connectives that we didn't get to last time, and then the rest of the time I'm going to talk to you about something in two-dimensional category theory that we can use to see the harmony of the propositional connectives more uniformly. Okay, so I remind you of this from last time, the definition of the product, so you should already have this. But now, through the magic of duality, my special dual pen here, I will now introduce to you the co-product. Okay, so if the product of A and B is a span on A and B, what do you suppose a co-product of A and B should be? Okay, it's going to be a co-span, whatever that is, right? But what that is a span, just with the arrowheads going the other way. Okay? So that for any other co-span on A and B, there's a unique T going the other way, such that T composed going the other way. So that's my circle composition. If you remember from the first day, somebody from the audience jumped the gun when I was explaining my left to right composition and really wanted the right to left, so now you've got it. So now this little diagram looks like this. Right? It's just everything I said about products, but switch the orientation of all the arrows. Okay? And before we said that A and B were called the factors of the product, so now they're called the cases of the co-product. The PIs were called the projections. I'll call them the insertions. Terminology on this varies, I'll warn you. And I'll refer to them generically instead of pies as little iotas, which I'm kind of bad at drawing, so let's see. Those are iotas meant to remind you of insertions. And finally, T is now the cotuple of the x's, and instead of writing it with these angle brackets, we write it with these square brackets. And now P is written instead of A cross B as a plus sign. Okay, so the reason that I want to sort of introduce this to you this way is to try to drive home the point that from the point of view of category theory, duality is a very powerful concept, right? As soon as we have one construction, one universal construction, we can automatically make a dual with no ingenuity needed whatsoever. It's just a purely formal exercise. You reverse the order of all the arrows, you reverse the order of all the compositions, and you turn the crank. Okay? So, now we had some lemmas last time about products, and we have their duals about co-products. Sorry, did someone say something? Okay. And the lemmas are actually the same lemmas, right? They're just the same lemmas, but in the opposite category. So let me just remind you what they are. We had identity expansion, which we got by probing a universal construction with itself, right? This was the Socratic method of self-knowledge in category theory. There was the uniqueness principle, which said, so in this case, this should say co-products up to a something preserving ISO. And what should that something be in this case? So in the case of products, if you remember, it was the projections that had to be preserved. So what's the dual of the projections? The insertions, exactly. And the proof is exactly the same as the one for product. So, let's see, I made a note to myself to say something else. Oh, right, and then we also have a coproduct functor. So this is the functor that goes from C cross C to C, where remember, we went through this little spiel last time with the products, that this is the product of categories that we defined on, I think it was the second day, right? But it's just the category consisting of formal pairs of everything. And this is the name of a functor from this category to well, one copy of C. And its definition on arrows, I'll leave that to you, I think it's in the notes, but if you feel ambitious, you can do it as an exercise to see what the definition on arrows should be. Right? We just defined the coproduct of objects, right? And a functor has two parts. It has to be defined on objects and arrows. So there's the part for objects, and then the part for arrows is dual for the case for products. Okay, so that's a whirlwind tour of coproducts, and you might feel cheated, but I kind of want to impress on you that that in category theory, the duality is like really all there is. There's no additional information needed. Okay, so that's more important than this, so I'm going to continue here. And now we have the information that we need to interpret our next connective. Which is disjunction. Right? So if we have a disjunction of two propositions and we want its interpretation, what do you suppose that should be? Well, prizes for guessing it's the coproduct, the interpretation. Okay, like that. Now we come to the rules, the inference rules. So the intro rules are pretty easy. So if you remember, we have from A, we can infer A or B. And from B, we can infer A or B. And I'll try to use the notation here. Or intro 0 or intro 1, I guess. And we interpret those as the insertions. Okay. And now we come to the other rule, and something slightly interesting happens. Something quite interesting happens, which is this. So let me write one version of this, and then we'll look at it and see why it's not quite right. So if from A, I have a derivation D0, from which I can infer C, and I have a derivation D1, which from B I can infer C, then I can cancel these assumptions, and from A or B, I can infer C. This is my hoop, or the. Okay, so this seems okay, and we can interpret this thing. As the cotuple. Right, so there might be other assumptions around, right, in the derivation. This might not be like the only assumption of the whole derivation. There might be other stuff. So to see that more clearly, let's write it in this localized notation that I've been using occasionally, and Frank has also explained briefly, right, for the turnstile symbol. So in the localized form, we have that from gamma together with A, we can infer C. And from gamma together with B, we can infer C. Then from gamma with A or B, we should be able to infer C. Right? That's the idea that we're trying to express here, right? Except now I've made explicit the assumptions. Okay. And I'll write this in a notation that's close to that, which is not quite legal natural deduction notation, but there's a method to my madness here. And it's this. So if D0 lets me conclude C from A, and D1 lets me conclude C from B. Oh, the whole point was to have gamma here, right? I should leave myself more space. Then from A or B, but now also with gamma, I can infer C. And I can cancel all of these assumptions. Right? So the point is, here I use one copy of gamma in each subderivation, but this rule is telling me I only need one copy of gamma overall. Right? And this morning, Frank started telling you about linear logic. And in that case, right, we might not be able to do this. If we only have, say gamma is $1, right? Can I do this? Let's see. Okay. Well, never mind. But the point is that you may or may not be able to use assumptions more times than once, right? So it would be sufficient. So okay. So the real rule, this one. That's the fake rule, which I should annotate, would be equivalent to the real one if we have this map that I'll call dist, which is for distributivity. So from X together with, so the product of X and the coproduct of A and B, this were isomorphic to the coproduct of the product of X and A and the product of X and B, right? Then the real rule and the context-free rule, the rule that doesn't account for an ambient context, would be equivalent. And let me try to explain to you why that is, right? So I could have here the product of X, A, and the product of B, like this. Now I apply my dist iso, and I get X cross A plus X cross B. And now this is a coproduct, so I know I have the insertions. And now C is what I'm trying to prove down here. Right? So if I can prove C from X and A with some arrow, and I can prove C from X and B with some arrow, then I know I have here the cotuple. And now I just compose it with my distributivity map. And so I'm okay. So the question is, why do we have this isomorphism in our category that we're interpreting our logic in? Okay, so in general, we might not, and I was thinking for a while about how I was going to try to explain this to you without going into a lot of stuff that we would only need in order to explain this, and I don't really have time to cover. But luckily, Bob saved my bacon because he explained this to you, at least in the pre-order case, I think in his first lecture, right? He talked about in the presence of exponentials that a lattice is distributive, right? Okay, so the idea is just the same. He called that thing the consequence of the Yoneda lemma, which it is, and I absolutely don't want to talk about the Yoneda lemma because that would be a lecture in itself. But the point is that as long as we have exponentials, which I haven't talked about yet, but I'm about to, this is okay. We always have this isomorphism. And furthermore, there's a nullary version of this too, right? There's also something that I call absorption, and it's an isomorphism from x cross 0, where 0 is the initial object, and 0. Right, so this is just like in arithmetic. If you multiply anything by 0, you get 0. And it holds for the same reason distributivity does in a category where we have something called an exponential, and that is what I'm going to tell you about next. So in a way, I'm kind of lucky to be giving this lecture at a programming languages school because as functional programmers, we're really used to the idea of currying, right? Once we get used to writing higher ordered functions, we start just thinking that way, and then we find languages that don't let us do that to be very cumbersome and restrictive. So the idea of an exponential is just the idea of a curry function, but it's given in a behavioral way, right? This is a universal property as opposed to assuming that what we have is a function. So an exponential of objects A and B is an object I'll call E, and arrow, which I'll call epsilon, going from E cross A to B. Okay, so that's the shape of this universal construction. I've been trying to impress upon you that every universal construction has some shape. And then the universal property says that for any other construction of the same shape, so now I have to say, so that for any object X and arrow F from X cross A to B. Let me change the pen. That's good. There is a unique map, which I'm going to call the lambda of F, for reasons that will be familiar to you probably, going from X to E, such that, now I'm going to write this out algebraically, but I'm going to draw a picture in a moment. Okay, so what this says, right, is that the data is we have an object E and a map from E cross A to B is called epsilon. Okay? Now, for any object A, for any object X, and map from X cross A to B, which we'll call F, there is a unique map from X to E, which we call the lambda of F, such that when we take the product of that with the identity map on A, right? So notice this is the dimensional promotion I was telling you about way back on the first day. this composition just gives you back f itself. Okay, so I want to try to impress upon you two things. One, that the form of this statement has the same form as the statements I've given you before about products and co-products, and in a slightly more trivial sense, terminal and initial objects, right? It's always something of some shape, such that for anything of that same shape, there's some unique map such having some property. Okay, and the second thing I want to convince you of is that this is what you already know as function currying in functional programming. So if we think of f as a function of two arguments, one from x and one from a, that gives you back a b, right? We think of this as the curried version of f that just takes the first argument and gives us back what we think of as the curried function. So that if we take that and we just do nothing on the second argument, and then we evaluate that curried function on the second argument, we get back the same answer that the original function would have given us if we had given both arguments at once. So do you see why this behavioral characterization of a universal construction, why function currying is an instance of this, why it's something familiar? Okay, so in this case, the map epsilon is called the evaluation map. And lambda of f is, it's usually called the exponential transpose, but there's no way I'm going to write that many times, so I'm just going to say the curry of f. And as you know, we can not only take a function and curry it, but we can uncurry higher ordered function, right? And the way we do that is if we have something already up here from x to e, to uncurry it, we just cross it with the identity on A and evaluate it. And then we get a function that wants both of its arguments at once. So currying is lambdaing, and uncurrying is crossing with the identity on A and evaluating. Okay, so we just met a new universal construction. So what does Socrates tell us we should do to it? Probe it. All right, so let's see what that means in this case. Okay, so here we have E cross A, B, the evaluation map. And now, what does it mean to probe this with itself, right? What do we set to what? So the things that we're universally quantifying over are the x and the f, right? So what should those be set to? How about E and evaluation? Okay, so here we do E cross A and go to B by evaluation. Okay, so the universal property tells us that there's a unique map from E to B, which is the curry of the evaluation map, such that when we cross it with A and evaluate it, we just get the evaluation map. Now, what possible map could there be from E cross A to E cross A, such that when we compose it with epsilon, we get epsilon? Okay, this has to be the identity, right? And we can see, in fact, that this has to be the identity by the uniqueness part of this universal property. There's a unique map that has this. If the identity here has this, if we cross the identity with the identity by the functoriality of the product, right, its action on arrows, that's the identity. So it must be, we've just discovered that lambda of epsilon is the identity on E. And this is called identity expansion. In this case, for exponentials. Notice I've been very methodical about sort of using the same pattern each time I introduce a new universal construction. I identity expansion now for all of the universal constructions that we've met. And then we have a lemma, which I'm not going to prove, but you should be able to guess the statement of, and this is the uniqueness lemma, and it says that exponentials are unique up to a something preserving ISO, and what should that something be? What's the structure, what's the shape of the exponential? Exactly, evaluation. Okay, so I'm not going to prove that at the board. It's in the notes if you care to look at it, or you can try to prove it yourself. It's not too bad, although it's a little harder than the others. Okay, so now I'm going to give you an exercise in the same pattern as before. So explain why is it that this equation holds in the diagram I'm about to draw. Okay, so let me draw the diagram. So we have from x cross A to B F. We have here from x to, right, okay. So because of the uniqueness, right, up to, so it's as unique as it can be by behavioral characterization, right, following pattern, we will write the exponential like this, or sometimes like this. Okay, so E, in other words, E is the exponential of A and B. I write this as an infix thing, usually because this thing, obviously it's hard to, if you try to compose it, then the superscripts get a little cumbersome. Right? Okay, and the reason I bring that up is because here, now I can go from, oops, where was I? Right, sorry. No, wait, now I'm confused. Ah, right, okay. So here, here's my evaluation map. Here's an arbitrary f. Here's its curry. Now I'm asking that if I precompose an arrow to this curry, which I'll call I, right, that that is the curry of I cross the identity on A. So that must go from Y cross A to X cross A, right? So, so in order to answer this question, basically you have to say why this triangle commutes. Okay, and the reason is because this composition has a unique curry, right, a unique adjoint transpose, such that if you take that thing and you compose it with the identity map on A and you evaluate it, you just get this thing. If this triangle commutes, then it answers this question. Okay, and now I'll give you a hint, right? What do we know? We know we can subdivide this triangle into here. I'll label it like this. And now we have two problems, right? Problem one, and oops, they can't both be problem one. Problem two. Okay. Can anyone see why problem one is easy? the universal property of the exponential for f, right? So basically, the part, what you have to do is figure out why triangle 2 convenes. So I'm going to leave that as an exercise. Okay, and now, just like with the product and the coproduct and, well, okay, there is a functor. Okay, so this is a lemma, something to be proved. That there's a functor called a, let's say this, the exponential of a to a, right? Now I have to tell you its boundary, so it's going from the category C to the category C. It's what's called an endo functor. Its action on objects is to just give you back the exponential, right, by a. And so now, what should it do on arrows? Well, what it does is call this, not surprisingly, but that's just a notation that doesn't mean anything. But what it does is it curries the evaluation map composed with G, right? And this I can't really motivate very well yet, but when we get to natural transformations, which should be like half an hour or less, I will be able to, but I can at least convince you that it has the right type. Right? So here, let's just look at what the types of these things are, by which I mean the boundary. Right? I have, so epsilon, the evaluation map, goes from the product of the exponential and a to b, right? G goes from b to c. And then if we curry that, then we get a unique map going from the exponential of a and b to the exponential of a and c. So it at least has the right boundary. But as for why this should be the definition, you have to wait a few minutes to find out. Okay, so we now can interpret our last propositional connective, which is not surprisingly implication. Okay, so if we have an implication, which, okay, notice that the same symbol is being used for the logical connective of implication and for the exponential. Depending on your point of view, that's either a happy or an unhappy coincidence, but I don't know, that's what I use. There are many variations. If we interpret this, what should we get? Well, I kind of gave it away at the beginning when I told you about how this is really function currying and functional programming, and we already know by the Curry-Howard isomorphism that that should be the same thing as implication. Okay, so we interpret the connective of implication by the exponential map. So now I have to tell you about the rules. There's the intro rule, which says that if from some derivation I can prove from A, B, then I can prove A implies B, and I can cancel this assumption A, right? That's a hypothetical derivation. But again, there's a problem here that has to do with the contexts. Right? So let's try to write this in local form, or localized form. Right? This says that if from gamma together with A, I can infer B, then from gamma alone, I can infer A implies B. So now we've made the context explicit. Okay, and now in the sort of not quite legit notation that I've been using, I can say, sort of combine these and say if from gamma together with A, I can infer B, then I can cancel those assumptions, and from gamma alone, infer A implies B. Okay, so these are kind of different ways of expressing the same idea. But the point is that the interpretation is, over there, okay, so the interpretation of the introduction rule should be recurring operation. Does that make sense? Okay, and there's one more rule, the limb rule, which says that from A implies B and A I may infer B. And its interpretation should be, well, can you guess? What do we have that lets us do that? And the evaluation map. Okay? So that's now an interpretation of the intro and the limb rules for all of the propositional connectives of intuitionistic logic. So I haven't yet told you about the rest of the proof theoretic behavior, that is the derivation conversions, but that's coming. Let me just give you a little bit of terminology. I know you must be begging for more terminology. Sorry, I didn't make this stuff up, but whenever something becomes an idea that's useful enough to say in a way that's shorter than the definite description of it, then it gets a name and add more vocabulary. So, categories with the following structure. If we have a terminal object and products, so that's the same thing as having finite products, right? Those are called Cartesian. If we have, in addition, exponentials, those are Cartesian closed. If we have an initial object and a coproduct, that is finite coproducts, those are co-Cartesian. And if we have both initial and terminal, and both coproducts and products, so that is if we have finite coproducts and finite products, then those are bi-Cartesian. And finally, if we have everything, those are bi-Cartesian closed. Okay. So I will occasionally use these words so that I don't have to use all of these words or symbols. Okay. So this concludes the interpreting propositional connectives and their introduction and elimination rules portion of the program. Does anyone want to ask any questions before we start talking about derivation conversion. Yes?
So to do the interpretation that we've been doing, we require a bipartition closed category.
Yes, so that's a good observation. If we want to interpret intuitionistic propositional logic, we need at least a bipartition closed category, right, to interpret all of the connectives that we want. But I have not yet shown you that such a category also interprets the derivation that Frank showed you. That is the local reductions and the local expansions. So that's coming. But at least for the intro and the liberals, yes, this is what we need. Anything else? Okay. So when we started out, I kind of gave you this motivation that one way to think about category theory is as a reimagining of set theory, where instead of the primitive notions being set and membership, they are set and function, generalized to object and morphism, right? So at least in one sense, what we did was we took something that was zero-dimensional, discrete, that is sets, and we studied it formal system that's one-dimensional. So it has objects and it has arrows. Okay, so if we want to study categories themselves in a behavioral way, then at least by analogy, it seems like we might need to add another dimension, right? A two-dimensional thing to talk about the relationships between the one-dimensional things. And that is indeed the case. So one way to characterize this thing is like this. For parallel functors F and G, whose domain category is C and whose codomain category is D. A natural transformation from F to G, to give this a name, I'm going to refer to it. Let's call it phi. Has the following structure. For each object, A, in C, an arrow in D, so an arrow which is called phi of A in D, from F of A to G of A. Okay, this is called the component. So phi of A is the component of the natural transformation phi at the object A. And further, for an arrow, F in C, from A to B, what's called a naturality square, which I'm about to draw. And that says this. So let me present it this way. In the category C, we have this arrow from A to B called F. Right? Now we have two functors going from the category C to the category D. So let me draw you a different diagram here in the category D. In one case, we have F of this arrow, right? So that's F of the arrow, which is going from F of the domain to F of the codomain. But we also have another functor, G. So there's the G image of this arrow, going from the G image of the domain to the G image of the codomain. And we also have, I just defined, these arrows in D, right, which go from the F image of an object to the G image of an object. So that's the component at A, and that's the component at D. And the naturality square, the naturality condition on this square, says that this diagram in D commutes. This square commutes. Does that make sense?
So by as an naturality square, you just mean
Okay, so
this is true.
yes, I mean, so this is the naturality square, and I'm asserting that f of f followed by phi of b equals phi of a followed by g of f. But rather than writing it out as an equation, which doesn't give you a lot of intuition into what's going on, I construct it as this inevitable square that must arise if we take the two functor images of this arrow and the two components of the domain and codomain, right? So we can ask logically, what do we know about this square? And the answer is that it has to commute. Okay, so this is one way to present natural transformations. It's usually the first definition you see in the category theory book. It's also one that I don't really like because it doesn't have a lot of insight. It doesn't give you a lot of insight into what's going on. So let me try to briefly explain this. I really hope that I could talk more about two-dimensional category theory, but it's just not possible in the amount of time that I have. But let me tell you a little story anyway. So last time I told you about Socrates, who was a Greek philosopher. Today I'm going to tell you about Plato. He's another Greek philosopher. He wrote a book called The Republic, which contains a lot of crazy stuff. One thing in it that I like is he said people should study math for 10 years. I think this would be great for my employment prospects as a mathematician. But anyway, another thing that's written in that book is something called the Allegory of the Cave. And this is a story about which people are, for some reason that's not entirely clear to me, trapped in a cave. Not only trapped in a cave, but they're sort of chained in place and stuck staring at a wall. And behind them there is, I believe, a fire or something, creating light. And some people that for reasons I also am not clear on, like take objects and hold it between the fire and the wall and cast a shadow on the wall. So the people who are stuck in the cave, staring at the wall, see these shadows on the wall, and they hear, like people talking and stuff happening, so they hear sound. And so they think that the images that they see on the wall are like reality. They think that the world is shadows on the wall because they're not allowed to turn their heads. Okay, so why do I bring this up? Oh, and also, in the end, someone called a guardian comes and rescues them, and they like stumble into the light and see the three-dimensional world. So this is kind of the two-dimensional world of shadows on the wall. So in fact, it's a one-dimensional world with shadows on the wall. It's even worse, right? So these components and naturality squares that we see projected into D is the wall in my analogy, right, are really something like this. So in the category of categories, or small categories, let's say, right, we have C and D, and we know we have functors here, F and G. And what's sort of really going on is that phi is a two-dimensional arrow between these two one-dimensional arrows, between the categories C and D. And this setup actually is much more general than just, so we can imagine this going on in CAP. This setup is something that is not only true of the category of small categories, but we can describe it behaviorally in anything that is called a two-dimensional category or two-category. Well, okay, I'm not being exactly precise here, but for purposes of this lecture, it's sufficient, right? So we can define this whole setup behaviorally, rather than this, which is structurally, right? We're saying we're saying exactly which shadow phi casts in D for each thing in C, each object in each arrow. But in order to do this is structural because we're looking into the categories C and D to see what's going on inside. Whereas behaviorally, we would just consider C and D to be opaque and look at what's going on between the arrows between them. Okay? So now that I've told you this lovely story, I unfortunately have to tell you that I will not be able to rescue you from the cave during this lecture. But if you look at the notes, there's a pretty long section about this stuff, so you can rescue yourselves from the cave later.
Good question. In your last diagram, why the arrow goes only from F to G? If there's an arrow another way around from G to F?
Well, in this case, because I said a natural transformation D from F to G, so that's the orientation that I gave it in the statement. If you're asking, should there be a natural transformation going the other way?
Yeah.
So not necessarily, right? These things are oriented just the way arrows within a category are oriented. It may be an isomorphism, that would be called a natural isomorphism, and that's a thing, an important thing. But it may not be. In general, these are directed, and not every morphism is an isomorphism. Okay, so let's carry on. Okay, so the reason that I bring this up is I want to tell you about something called an adjunction. And the reason that I've been describing all of the universal constructions that interpret our connectives in this sort of very maybe tedious but uniform way, right, where I introduce the universal construction, we do the identity expansion by self-probing, we do the uniqueness condition, we do all of these things sort of in the same way for each one, is because all of these constructions are actually just instances of one construction. And that's what I want to tell you about. So that thing is called an adjunction. There are several definitions of adjunction that are equivalent to each other, and I'm not going to have time to prove the equivalence. So I'm going to give you basically 2.5 today, and I'll explain why I say that in a moment. And different characterizations will be useful in different circumstances. So the equivalence is something, it's a proof obligation that I'm not going to fulfill. You're going to have to go look that up yourself. So functors, F and G, these are anti-parallel functors, I should say. Form an adjunction, which is written like this. That's F backward turnstile G. And then the notation, or the terminology here is F is the left adjoint in this adjunction, adjoint, and G is the right adjoint. If for any objects A in C and B in D, so now I have to give these things names. Okay, so F is going from C to D, and G is going from D to C. Okay, that's what makes them anti-parallel. We have a natural bijection of onsets. Okay, what on earth is that? Well, first of all, it's a bijection of onsets. So this says that, so this is my symbol for bijection. For any arrow in C from A to G of B, there is a unique arrow in D from F of A to B. Right? That's what makes it a bijection of set, right? This is a home set, this is a home set. I'm saying that there is one-to-one correspondence. Okay, so in my notation, which is, there's diverse notation on this, so you're stuck with mine for today, I will call the downward arrow of downward direction of this bijection sharp, and the upward direction flat. So like music, right? And this is a bijection, so if I have an arrow here F, and I sharpen it, and then I flatten it, then I get back F, right? Okay, so that's the bijection part. Now I need to explain the naturality. Okay, so this says, that if I have some arrow here, let's call it F, and its partner under the natural bijection, or under the bijection is G, right? So in other words, F is G flat and G is F sharp, right? So I'm saying these two arrows are in bijection. Then I can extend this bijection along both the domain and the codomain boundary. So what do I mean? I mean if in C, I have another object, A prime, and an arrow little a from A prime to A, then in D, I can extend the bijection from F of A prime along F of little a to F of A. Right? So it's saying if these are the two arrows are a pair, then these two composite arrows are also a pair. So this is naturality in the domain coordinate, in the domain position, the domain boundary. And then the same thing holds over here in the codomain boundary. If I have an arrow little b going from B to B prime in the category D, then I can, and so F and G are still in bijection, then I can extend the bijection by doing here G of little b to G of B prime. Okay? This is a little weird, but it's just saying that if I find two arrows that are a pair under the bijection, I can extend that bijection on either side of the pair by, in one case, just composing an ordinary arrow on the side where I have just an ordinary object. And in the other side, I have to compose the functor image of that arrow on the side where I have the functor image of the object. It's a little weird, but it's not too crazy. Okay, so what's actually going on is that this is a natural isomorphism in a functor category, but I'm not going to talk about that. We're just going to leave it at this. And now, I'm going to give you another 1.5 completely equivalent characterizations. So F from C to D and D from D to C form an adjunction with F adjoint to G if either of these two things hold. The first one is called the universal property of the unit. This is the unit of the adjunction, which I'm about to tell you about. Okay, so this says that there is a natural transformation called eta going from the identity functor on the category C to the composition of functors, F followed by G, such that for any arrow F in the category C, between A and G of B, right, where A is an object of C and B is an object of D. Here's the unique arrow G and D going from F of A to B, such that eta of A, the component of that natural transformation, composed with a G functor image of little g, is equal to F. So what the heck does this mean? Right? This is pretty crazy. Let's draw a diagram. So what do I start out with? I start out with a natural transformation, eta, and I have an arrow in C from A to G to B, and that's called F, right? And now I have the component of eta as A, so that's going from A to, let's see, G after F of A. See what I did there? With a circle notation so I could write it on the left and make it look like a function. So that's eta of A. Okay? Okay, and now this arrow F has a unique arrow G living in the category D going from F of A to B. So this is the thing I'm asserting exists, this G, such that if I compose the component of A with the G functor image of this arrow, then I just get my original arrow back. Okay. So you can kind of see why this might be the same as the definition I gave you before, right? There's some kind of bijection of arrows going on here. And before I said that bijection was natural and what that meant in terms of extending along the boundaries, but that wasn't any concept that we could obviously identify as having seen before. But here is something I just told you about a few minutes ago, natural transformation. So it turns out that this natural bijection has a lot to do with natural transformations, but I don't have time to go into the details. Okay, so this is one of the two equivalent characterizations. The other one is dual. So by the way, in this case, this natural transformation eta, this is called the unit of the adjunction. And here, we will say F is left adjoint to G, where G is right adjoint to F. They form this adjunction if there is a natural transformation called epsilon going from G followed by F to the identity functor on D, such that for all arrows G and D going from F of A to B, there's a unique arrow F in C going from A to G of B, such that F of that arrow composed with the component of the natural transformation in B, it just gives us back our original arrow. So let's draw this. I'll put it over here. Right, so what does this say? We have in D an arrow from F of A to B, and that's called G. And now we're saying in C, there's a unique arrow going from A, oops, dash that, to G of B, and this is our F, right? Such that when we compose, so when we compose F of this, it has to go from F of A to F of G of B, right? This is F of that arrow, and I compose it with the component of the co-unit at B, and this thing. Okay? from the pictures, it's really clear that there is a duality here, right? Okay, what this duality is pretty interesting. I don't have time to talk about it too much, but the short version is, just as in one-dimensional categories we have a one-dimensional duality up, in two-dimensional categories we have another duality between two-dimensional arrows, and that's what's giving rise to this. Okay, so I know that was a big slog. Yes?
Wait, so you only need to do one of these things. Like, unit by itself gives you the adjunction, and unit by itself gives you the adjunction.
All three of these characterizations are like determine the same thing. If you satisfy one of them, you satisfy all of them. And okay, so why am I torturing you with multiple definitions of the same thing? It's because as we go, you'll see that one of them will be immediately applicable to what we're trying to do. And so rather than trying to like derive this at the time that we get there, I'll just say it now, and then it'll be easy like, when we try. So basically, I'm transferring the complexity from the point of use to the point of description. Right? So I'm saving you work. Okay, now I get to give you an exercise to make you work. So here I'm co-saving you work. This is another one of the explain why things. Okay, I'll just say explain why. If I take a component of the unit at some object, and I sharpen it, I take its adjoint transpose, then that should be the identity arrow on F of A. Right? So just like that. And similarly, if I take a component of the co-unit of the adjunction at some object, and I flatten it, that should be the identity of G, the G image of that. Okay? And I'll give you a hint. To probe these things with themselves. You'll never fail to learn something about something if you try to just apply its universal property and to substitute itself for the thing that you're universally quantifying over. Okay, so good. Why did I bring all this up? Read that. This. Let's look at implication again. So first of all, when we looked at implication the first time, we drew a diagram that looks almost exactly like this, right? The difference was both of these categories were the same, and we didn't have any argument to this evaluation map. In the exponential, the interpretation of the implication, right? So here, we have, you can see, we have an arrow from objects x cross A to B. Then in C, we have an object from X to A implies B. Okay. It turns out that we can describe this as an adjunction like this. So it turns out that this exponential functor that I defined for you, but I had a hard time trying to motivate, is right adjoint to this product functor, where we fill in one of its two arguments with the same object that we use to fill in the left side of the exponential. Okay? And the way we can see this, right, we've seen all of this before except for one part, so let me just explain that. Okay? The only thing that's different is now we're asserting that the evaluation map is a component of a natural transformation. And we didn't have the vocabulary to say this before. Right? And now if you go back and look at the definition I gave for the exponential functor on arrows, you'll see that it's exactly what's needed in order to make the evaluation map be a component of a natural transformation. So it fits together just perfectly, basically. Okay, so let's use this information to look at the derivation conversion laws for exponentials, or for implication rather. Okay, so I'm going to name these things cleverly. I'm going to call this commuting triangle beta sub r. I'm going to erase the other one. Okay, I would have called it beta sub L. Okay, and let's see what this commuting triangle tells us. Right? So it's telling us that if we query a map, cross it with the identity on an object, and then evaluate, we just get that thing itself. Right? So say we have a derivation d from gamma and a to b, and its interpretation is the arrow f. Right? So the interpretation of gamma is x. The interpretation of the proposition a is, well, happens to have the same name, but it's the object A in the category, and the interpretation of the proposition B is the object B in this category. Okay, so we take this, and we query it, right? That's what this says. So that means we can cancel these assumptions, and from just the assumption gamma, we can conclude A implies B. So this is arrow intro, sort of, in our slight variation. Right? That's the lambda, F. And now we cross it with the identity derivation on A. What's the identity derivation look like? It just looks like this, right? It has no inference rules. Its single assumption is the conclusion. And now what do? We do the evaluation map. But the interpretation, the thing that got interpreted as the evaluation map was just the enumerable. Cool, right? So that's this. So going around the long way on this triangle, if we sort of uninterpret it back, if we uninterpret the categorical semantics back into the natural deduction, says that this thing, that this composition is represented by this derivation. Right? If we interpret this derivation, we'll get that composition, is what I'm saying. Okay. But now, what if we interpret the other side of this commuting triangle? Commuting diagram. That's just F, right? And F was just the derivation from gamma and A, which I call D, to B. So what have I just learned? Yeah, this is the local reduction. Frank called this like this, with an R. This is the local reduction for implication. Okay? So the local reduction for implication is just witnessed by the fact that this triangle commutes. Okay? Let's press on and see if we can interpret some more derivation conversions. So there was the local reductions, but then there was also the local expansions, right? So what was the exercise that I gave you before about the adjoint complements of identity morphisms, right? So in this case, it's that the identity of a exponential, right, should just be the Curry of the evaluation map. And we learned this also before when we probed the exponential with itself, right? This is what we learned. This was identity expansion. Okay, so let's see what this says, right? So if we do the identity derivation on this implication, it just looks like that. And on this side, it says first I take the evaluation map, so that goes from A implies B and A to B. Right, that's the evaluation map, which is also the lim rule. And then I curry it. So how do I curry it? I cancel the assumptions, and I get to apply the introduction rule to go from the assumptions minus the A to A implies the conclusion. So what have I built now? It looks like a local expansion, but it's a local expansion only for an identity derivation. Right? In general, in Frank's setup, we had here an arbitrary derivation E, and we precompose it, right? So in this notation, it's a little, the notation doesn't quite match up because we don't see, so I've been writing sort of off to the side here just the global assumptions. And when I precompose something to the global assumptions, it's not clear what I really want is to get it. I want this E derivation to be moved up here. So the question is, why am I allowed to do that? Why am I, instead of having that, why can I have this? So this has some assumptions, let's say gamma. So why can I do this? And the answer is the naturality of the bijection of the Hom sets in its domain coordinate. Okay, so in an adjunction, we know that the bijection, okay, so here's what I mean. If I have the, okay, so in the exercise I gave you for, I think I called it precomposing the Curry. If I had I compose lambda F, right, this was the diagram of the two triangles that you had to prove commuted, and one was easy and one was hard. Okay, so let's see what this says if we write it in a natural deduction style notation. Right, so if we take a derivation D, to interpret as the arrow F, and we curry it, then I can infer, oops, yeah. This, right, this is interpreting, so D is interpreted as the arrow F, lambda F interprets the implication introduction of that, and now I precompose that with an arbitrary derivation E, or gamma. Okay, so that's the left side. And the right side says that first I take, okay, so let's do it this way. First I take F, so that's the D going from C and A to D, and I precompose it with E across the identity on A, so nothing happens here. So this is going from gamma to C, right? And then I curry the whole thing. So that's the arrow of the intro. And then I just take gamma here, I get to cancel this, and then I get A. So basically, if this is making any sense to you at this point, the naturality of the Hom-set bijection in the domain coordinate lets me take an identity derivation expansion and turn it into an arbitrary local expansion. Okay, so for the negatively presented connectives, this is like not so clear from the syntax of natural deduction, but for the positively presented connectives, it is. There are these things called permutation conversions, and they are an equivalence, they generate an equivalence relation of derivation. Okay, but I think I should stop soon, so let me tell you sort of the punchline for the day. And that is this. The fact that this works for this connective isn't just sort of an accident or a coincidence, right? It ends up that it works for all of the connectives of intuitionistic propositional logic. And for the negative connectives, it turns out that they are interpreted by right adjoint functors. And they have the property that their intro rules are interpreted, the negative one. Their intro rules are interpreted as the flat direction of the natural bijection. Their lim rules are interpreted as the component of the counit. Their local reductions are interpreted as this thing I call beta sub r, the commuting of the triangle here, the universal property of the counit. And their local expansions for identities are interpreted by what I call the identity expansion. I'll just call it identity expansion. So this is what we learned by self-probing, right? And then for the positive connectives, I didn't write it down, because I guess you're probably good to go. But there's something that's quite dual. So there, the introduction rules are the unit of the adjunction. The elimination rules are the sharp, natural bijection. The local reductions are I didn't write it down, but it's beta L, the commuting triangle in the universal property of the unit. And the identity local expansions, they are what we also call the identity expansions when we did the self-program. Okay, so that's the story I want to tell you for today. The big picture is that this one idea of an adjunction can give you, in a uniform way, the structure of all of the connectives of intuitionistic propositional logic. And tomorrow, I'll talk about dependency in category theory and how we can use it to interpret the first-order quantifiers of first-order intuitionistic logic. So I'll stop there, and if there are any questions or comments, we can do that.